All right, so this week, what are we doing? This is what we're going to be working towards, dark matter. Right? We're detecting dark matter this week. That mysterious, elusive stuff that makes up 3/4 of our universe ball. It doesn't make up dark energy. That's not besides the point. Weird stuff, weird goofy stuff is going on, and we're going to figure out what it is, potentially, and we're going to identify that it's there. All right, so the rotation curve and mass of the galaxy, dark matter. The purpose of this lab is to literally weigh the galaxy. We're going to take measurements throughout our galaxy, throughout the visible region and beyond, and we're going to use those measurements of speed at various radii throughout the galaxy to make a measure of the mass contained within various radii. And if we know that, and we can plot these things, then we can make a measure of how much mass is there in the visible region of our galaxy. And presumably, since we're talking about dark matter, we're going to find some mass that is in non-visible regions, right? So we're going to see that there's something there that shouldn't be there, or that we don't see. Something that we're finding mass for that we can't actually see. All right, so that's the basic outline. That's our 3 major talking points. Measure speeds, make a rotation curve, and use it to find the concentration of mass in our galaxy. Is it concentrated at the center, like in the solar system, or is it spread out uniformly in the disk? And then to measure the mass of the galaxy and determine if we can see if it's all accounted for by the visible matter, which you can probably guess it might not be. All right, so if we want to go and make measurements throughout the galaxy and use those to make observations to determine speeds at various points, various radii, presumably we're going to be looking all throughout the galaxy, but there's an issue here. If we look down the plane of the galaxy, this is what we see. All right, so if we look at all the stuff that we think of stars, the usual things that you would try and track motion of, we have something that we run into, which is all this gas and dust in the plane of the galaxy. So it makes it really difficult for us to make observations at visible wavelengths. All this light is obscured in the plane of the Milky Way, and so we presumably have to go to another part of the spectrum in order to make these measurements. Luckily, we have parts of the spectrum that are not impeded by gas and dust, namely radio waves. Radio waves have longer wavelengths, and so they just keep on trucking. They go right through all that gas and dust. That's why we use them to send signals here on Earth, because they're pretty unimpeded, and they just go. And so it also turns out that there's an abundant source of radio waves within the plane of the galaxy, and that's from this transition. Okay, so I think you guys talked a little bit about atomic transitions in 101 maybe, and this is not an atomic transition. It's not an energy level transition. So it's not like if you had an excited atom that went to a lower state, a lower energy level, and emit that energy as some photon. This is a lower energy sort of emission that we're talking about. It's from random spin flips. So if you have a hydrogen atom, it's just a proton and an electron. And those objects are charged, and so they have magnetic fields. And if the magnetic field of these two, the proton and electron, went from being aligned, so their north poles or south poles are pointing in the same direction, to being anti-aligned, so their north and south poles are pointing oppositely, like this, that releases energy. All right, just like if you had 2 bar magnets, and you try to put the positive poles together, that's difficult, right, or the negative poles. They want to resist that. It's more favorable to have the opposite poles aligned. And so going from this aligned state to this oppositely aligned state releases energy in the form of a 21 centimeter photon. And this is an abundant source of radio waves. It's a relatively rare transition. It only happens every 11 million years. It's just a random flip that happens. But it turns out that there's a heck of a lot of hydrogen, cold hydrogen, in the plane of our galaxy. And so we see a nice bright glow at this wavelength. This is just a map of 21 centimeter emission. And you can see all that obscured regions of the galaxy in our disk are now glowing beautifully bright because of all that hydrogen. There's just so much of it that it doesn't matter that it only happens once every 11 million years when you have not that much of it, billions and billions of grams of it. All right, so now we know we have an emission source that we can look at. We need to make some measurements. We need to quantify what we're looking at. So we take spectra. And so if we just look right down the pipe toward the center of the Milky Way galaxy, what do we expect to see? So to figure that out, we take a top-down view. So this is a view of the Milky Way galaxy. And this dotted line is our line of sight. All right, so we're looking right toward the center of the galaxy. The arrows that you're seeing here, to the left and to the right, are the velocity directions of these various pockets of gas and dust and light on these spiral arms. All right, so each of these spiral arms is moving. It's rotating around the center of the Milky Way galaxy as it spins. And so they have velocity components in this direction for all these ones, and in that opposite direction for all these ones. And so the net effect here is that none of these little branches of these spiral arms that we're looking at emission from all these sources of cold hydrogen. None of them has a velocity component which is directed toward or away from us. That's important. So they're directly perpendicular to our line of sight, which means that they're not going to be, all their velocity component is to the side. We're not seeing any of that motion, which means there's not going to be any net Doppler shift. Should I skip right over the Doppler shift section? I did. Oops. Sorry guys, let's back up. I know you've talked about this, but we'll go over it again real quick. All right. So Doppler shift, we saw a little preview. We're going back to the core physics. Doppler shift, if you have some source of emission, and it has some emitted wavelength. If that source is in motion, the wavelength changes. Right? So that's what we mean by Doppler shift. If it's moving towards you, you see a blue shift, higher energy waves, or a higher energy emission. And if it's moving away from you, we call that a red shift. The wavelength gets longer, gets lower energy. Pertinent examples of this, you guys have all seen this. If you ever see it, hear a siren go by, right? As it's approaching you, that frequency, that pitch increases, and then as it goes away from you, it gets lower, lower, lower. So you guys all know what this is intuitively. If you wiki Doppler effect, they have all these nice little GIFs, these little animations. And so what you're seeing is that as an object moves, if you were over here, you'd see that it's actually catching up with the waves that it's emitting. Right? It's continuously emitting some source, whether it's sound or light or whatever, radio waves. And as it moves towards you, it's catching up, and so the wavelength is getting shorter. If you were over here, it's actually emitting them further and further away from you. So this wavelength is actually expanding. Just found that in either case, what we're interested in is a change in wavelength, and that's the shift that we're talking about. So the change in wavelength is equal to the emitted wavelength times the change in velocity over the speed, in this case of light. It's the speed of emission. So if it were a sound wave, it'd be the speed of sound. In this case, we're looking at electromagnetic waves, so it's speed of light c. The important thing to note here is that delta v is the difference. Right? If I'm moving and that object's moving, it's our relative velocities. Right? If I'm moving at some speed, if I'm moving at 100 kilometers per second, and it's moving at 100 kilometers per second directly away from me, you're not really going to notice anything. If it's moving away from me with some net speed or toward me with some net speed, that's what we're measuring. We're measuring the difference in velocities. That's important because we're actually moving through space. Right? We're on one of those spiral arms. We're rotating around the center of the Milky Way galaxy. And so when we measure a Doppler shift, we're actually measuring a net difference in velocities. It's going to be important in a second. The other thing to note is that delta V is the component along our line of sight. So if it's moving in some direction, not directly toward or away from us, what we're actually measuring is the component in our direction. So we're going to have to get into a little bit of trigonometry to make some of these calculations later. Don't worry, it's all pretty well laid out for you. All right, so we talked about our 21 centimeter emission. So now getting into these velocity components probably makes a little more sense now. You notice that these are neither toward or away from us, and they're also not at some angle, so they have no component toward or away from us. They're directly perpendicular. So we don't see any Doppler shift. We don't see any change in velocity. And so what we observe when we take a spectrum, just the flux at various wavelengths, is that we should be seeing a strong signal at the emitted wavelength of this cold hydrogen gas. And that's in fact what we see. The wavelength emission is 21.1061 centimeters, and so in this case, when we look at a longitude of 0 directly toward the center of the galaxy, we see that the observed wavelength is exactly equal to the emitted wavelength, which is what you would expect. There shouldn't be any Doppler shift. But if we move off to some other galactic longitude, all right, instead of looking toward the center, we're looking off to the side somewhere. we should expect to see some net Doppler shift, right? We should expect to see that they have velocity components that have some amount toward or away from us. And so if we look at off to the side, some other line of sight other than toward the center, we're noticing that, okay, this is our motion in this direction. This pocket of hydrogen is moving in this direction. This pocket's moving in this direction, et cetera, et cetera. So these all have some component along our line of sight. The key here is this one right here. And what's important about this pocket of hydrogen? What do you notice about this arrow? Which way is it pointing? Relative to us. Sorry, directly away, right? So this is going to have the largest net change in velocity relative to us. That's the most important thing that we're need to take out of this. When we look along some line of sight, we're measuring emission, hydrogen emission from all 21 centimeter emission from all these pockets of cold hydrogen in each of these spiral arms. But the key is that when we look at our graph, we're going to see the most redshifted signature from this point right here. And that's the fundamental thing that we need to understand going forward. All right? Because we know it's coming from here, we can use some very basic trigonometry to figure out the radius at that point, to figure out the velocity components at that point. And we can also, when we look at our spectra, we know exactly which peak is the one that we're interested in. So let's take a look at an example spectrum. In this case, we're looking for the most redshifted peak, and so we want to go to the highest wavelength and figure out where that is. So this peak right here, all these little peaks are emission of cold hydrogen gas, right? But this one is at the highest wavelength because it has the largest net velocity relative to us. The one's moving directly away from us. One thing that's important to point out here, in this case, the most redshifted peak is also the strongest signature. But that's not always going to be the case, right? So we'll take an example right now. There's at least one or two of these I can show you. All right, so in each of these, the most redshifted component of this spectrum is not the strongest. It doesn't have the highest flux. All right, so notice that the highest flux is here, but there's a signature out here that has the highest redshift. By highest redshift, I mean highest wavelength. All right, so whenever you're making these measurements, you want to look at the graph and say, okay, where's the peak that's furthest to the right, in this case, which is at the highest wavelength, and you want to measure the wavelength of that peak. This is not super distinct, it's not like this, but this is, if this weren't a source of emission, this would just continue straight down. The other thing is that you're not worried about this little noise right here, this is just background noise. That's not a contribution from cold hydrogen. Another one's kind of, I guess it's burning. So again, just to illustrate the point, you have a very clear peak here that is not the tallest, but it's at the highest wavelength. It's the most redshift. Just make note of that. There's a couple of these spectra that, if you went for just the tallest one, it would throw off your results considerably. So we're going to be interested in a number of spectra at various longitudes throughout the Milky Way galaxy. We're going to measure the wavelength, the observed wavelength at that most redshifted peak. And since we know how to correlate change in velocity, back up to this beginning section. Change in velocity with the change in wavelength, if we measure some observed wavelength that's different from the emitted wavelength, we can figure out a change in wavelength, which allows us to compute a change in velocity. So that is the name of the game. This allows us to build a rotation curve. Right, so a rotation curve is a graph of velocity versus radius. So we're going to look at different regions, different lines of sight. We're going to use that to measure a change in velocity and figure out what the velocity is as well as the radius is for those locations. Okay, so we know how to compute a change in velocity. How do we get to the final value for the velocity, and how do we know what the radius is? So this is where the trigonometry comes in. This isn't a great graphic, but it's probably going to be easier to see when you actually pull up the lab. It's just a little bit smaller. So if the line of sight to the center of the galaxy is a longitude of 0, right there's the galactic center, if we go off to some other line of sight to the side, they'll be at some other galactic longitude, whatever it is. And we're going to tell you which longitudes to look at. Then it turns out that if our radius from the sun is this, the hypotenuse of this right triangle, then this component, the radius of this most redshifted region, is the radius of the sun times the sine of this angle, the sine of the longitude. What about the orbital speed? So we just talked about the change in velocity. Again, delta v is the net velocity toward or away from us. We're moving, so we need to add that component to get to the actual velocity of that most redshifted region. So we can figure out an observed wavelength, read that off our chart. One thing to note about here is the scale on the wavelength here. This is 21.10. This next hash mark is 21.11. So you're reading each of these tick marks is a change in the thousandths place. Right, so this is 21.101, 102, 103, etc. 21.110, 111, 112. Just sometimes when you go to make these measurements, that gets a little tricky at first. The way I would recommend doing this is pulling up each spectra on your computer and then just taking like a piece of paper or a ruler or something and holding it in line with that peak and reading off what that is. In this case, it's like 21.1115. Right. So once you have that, you know the observed wavelength, you can figure out the change in wavelength, you can figure out the change in velocity. We need to add to that our component of velocity along that line of sight. Right? So we're moving with some velocity in this direction, but we're actually measuring here a difference in velocity between us, our component in this direction, and between their true velocity. And to define the most redshifted region's actual speed around our galaxy, we need to add in v sun sine L, that's our velocity, times the sine of the longitude angle. And that gives you the total v. Right? So all this you're going to do very straightforward. We have all the spectra for you. I'll show that in a second. Before we get into, actually, there's one last background section we're going to go through. So I said that we're going to weigh the galaxy. Well, how are we going to do that? If you know the velocity and the radius at which something is orbiting a central body, it's pretty easy to figure out what the mass is. So let's just take the example of our solar system. We have a happy little sun right here. We take some planet in orbit. That's kind of a circle. This is the Earth. Earth is moving in this direction. So we can figure out what its kinetic energy is, or its acceleration. But what's keeping it along this circular path? Its velocity at any point in time is in this direction, but it's moving around in a circle. It's doing that because of what? I think I heard gravity. So we have gravity, which is in this direction. So in order to figure out basically a relation between the mass of the central body and the velocity and radius of this object, we just set up an equality. So we have m, the mass of Earth, v squared over r. That's its acceleration. We just set that equal to the gravitational acceleration g, which is a constant. The mass of the sun times the mass of Earth over the radius squared. And we just cancel terms. Turns out that it doesn't actually matter the mass of Earth or the mass of whatever's in orbit. It doesn't actually matter until we can find that m is equal to v squared r over g. So if we have something in orbit at some radius, whatever it is, with some velocity, we can figure out the mass that is required to keep it in orbit at that radius with that velocity is given by that formula right there. All right, so this is important. If we just measured a rotation curve for various points throughout our galaxy, which means we know two things. We know the velocity, and we know the radius of all those points. And so now we can just quickly use our mass formula based on those measurements that we just made to figure out what the mass is at those various radii. So presumably we've made measurements throughout the galaxy, so we can use those to weigh our galaxy. So one of the other questions that we wanted to know was the mass distribution in the galaxy. What do we know about the mass distribution in the solar system? Most of the mass is contained within what in our solar system? The sun. Something like 99.99% of the mass of the entire solar system is just the sun. All right, and so in that case, we make a rotation curve, we make a graph of velocity versus radius. We find what's called a Capillary rotation curve, which is this dashed curve A. So as you go out to greater distances, the speed decreases, it falls off. And that's because the closer you are to that central body, the faster we'll be moving. If you've ever seen animations or scale models of the solar system, Mercury is like whipping around the sun super fast, and Uranus is like barely moving at all. So that's because we're in Capillary orbits. Curve B is called a flat rotation curve, presumably because it peaks up to some value and then stays flat. And what this tells us in this case is that the mass is distributed throughout this system. All right, so if we make a rotation curve for the Milky Way and we find that it is flat, that means that mass is distributed throughout the galaxy. So that at every radius there is enough contained mass to be going at a pretty constant velocity. So you're going to be doing this, and you're going to determine whether or not the Milky Way obeys Capillary orbits, or whether it obeys this kind of flat rotation curve. Once you've done that, we can also make a graph of mass versus radius, and you can literally weigh the galaxy out to various radii. So you'll be asked to make that graph and figure out how much mass is contained within a certain radius, like the visible region. And then we're going to give you some measurements for the large and small Magellanic Cloud, and those will extend out to much further radii. And you're going to figure out, is there a lot of mass in between our visible region and these faraway things? If you do, presumably there's something that you can't see that is contributing a large amount of mass vis-a-vis dark matter. Okay, that was our background. Everybody take a deep breath. Some jumping jacks if you need to. Procedure is short and straightforward. So we have taken a number of these spectra for you. We go down to Green Bank, West Virginia, to the National Radio Astronomy Observatory. It's where the largest fully steerable telescope in the world is. None of the two pictured here. One other just little tidbit about NRAO. So this is the former Green Bank telescope. It was a 300-foot diameter. It's a football field up in the sky, essentially. Telescope, and it collapsed sometime in 1988. We actually got a story from the operator who was in the room when this happened. And apparently, he just heard what sounded like thunder and like shaking, like maybe he thought it was an earthquake or something. And it was the middle of the night, so he went outside and he kind of looked around, and you know there's like a door right here. So I assume he just walked out and then drove down the road and had absolutely no idea the telescope had collapsed on him. Until he came and was like, oh, my 300-foot telescope fell down on my head. Just had no idea. I thought that was funny. All right, so procedure. It's laid out pretty well for you. There's 5 steps for these 5 columns. So you're just going to make these observations. You're going to pull up each of these numbers on the side for various longitude. Pulls up one of those spectra that I showed you. I'll just click on one. It's linked. So you're going to pull it up. That was a good one. We'll measure the redshift of the wavelength of the most redshifted peak. Write that down or put it into the table. And then use that and all the formulas that we just went through to calculate the change in velocity, our component of velocity along that line of sight, so at whatever longitude, the total velocity, and then the radius. All right, so you really only have to make this first column of measurements. That's the only actual measurements that you have to make.
Can you go back to that picture?
Yes. This one?
Yeah, so the peak there, you pointed. So like you see how it kind of goes up a little bit to the right though? That one?
Right here?
Yeah.
Yeah, I mean, this is kind of where it's up to you. I would say this is more significant. This kind of looked like it's just maybe noise. You know, there's always usually going to be some bumpiness. You see it kind of bumpy throughout here. So I would say stuff that's more distinct, like an actual jagged peak, is what you want to measure. Any other questions on taking those observed wavelength measurements? Good question, thank you. One thing I think will make this easier, so last week I showed you how to do some calculations in Excel. If you go to the main Skynet Astronomy 101, this is kind of the old site, but it still has some materials that are useful. If you go to the labs page, there is a link next to Lab 7 for a spreadsheet. And if you download that, it just looks like this. And so this has both data tables that you're going to need. It's broken up to 2 sections in the lab, but it's all in one here. All the stuff to build your rotation curve, and then there's a separate table in the lab that's the same one here to compute the mass, enclosed mass. And so I would recommend, and for anyone who wants to do this, I'll kind of do a separate little Excel talk afterwards. Anybody who thinks they can either want to calculate by hand or doesn't want to sit around and listen to me talk about Excel, I don't think. You can go home, but I just think it makes the calculations a lot easier to just enter it all in here, enter in your formulas, and then copy it down. One caveat, if you are going to use this spreadsheet, and you are going to use the constants that you give you, the emitted wavelength is 21.1061. Okay, so for whatever reason, the spreadsheet only has it out to the third decimal place. So be sure to change that if you use the spreadsheet. Right, that's important. It will throw off your calculations enough so that you will lose points. So if you use the spreadsheet and if you reference the constants given in the cell, change it before you make all the calculations. Oops. All right, so you're going to measure your observed wavelengths, run through the calculations. It'll ask for a bunch of example calculations like you guys are used to. For the 84-degree line of sight, so that's this last row. And then it asks you to build a rotation curve. And do we live in a Capillary or a flat galaxy? And then what does that say about the concentration of mass? Pretty straightforward. The next thing you have to do is just make the mass calculation. So again, the formula that we have over there. And he gives you the gravitational constant in the appropriate units. So make that calculation. And we include measurements for this large and small Magellanic Cloud. So these are nearby objects. And so we can't make measurements beyond a longitude of 90 degrees. And so this kind of extends our scale. We know velocity and radius measurements from the center of the Milky Way for these. So if we graph those along with our mass measurements inside the galaxy, we can kind of see how mass is distributed out to those great distances. And if all we see is the visible region of the galaxy and then this tiny amount of light out there in the large and small Magellanic Cloud, and mass continues to grow in between there, presumably there's something going on. So this is where you weigh the galaxy and figure out whether or not there is dark matter. So we'll ask you to make a graph and estimate the mass of our galaxy within various radii. Is the mass outside the visible part of our galaxy less or more than the mass inside? What does that say about dark matter? And then the last question is to research and discuss what dark matter, at least in our galaxy, might be. So in this case, it's fine to just Wikipedia dark matter, but go beyond the intro section, right? He wants to know what dark matter candidates might be. So there are different things that are theorized to possibly be the source of dark matter. You will get the full credit if you go through the steps of actually researching what those are and naming what possible candidates are. You just say dark matter is theorized to make up some percentage of the universe, you're not going to be able to. It's just my caveat there. For anybody that wants to, well, we'll see how many people want to do this in Excel, and if so, I can do it up here, or I can come around and work with you in groups. Whatever's good for you guys.
If you do it in Excel, you have to change it.
So, you can get into this now, but if you do it in Excel, anything, so you have a couple calculations that are based on the longitude that you're looking at. These are given in degrees. Excel's sine function is expecting an angle in radians. So this has to be converted first. Excel has a function to do that automatically for you. It's called radians. But just setting it up is a little bit tricky, so happy to go through that with people. So I'll take a little break from my talking for a second. If anybody wants to leave, feel free to move on. Any other questions before we get going? All right, I think that's all. That's all I got.